So we've been looking at how language can be modeled using transformer architectures, and we've also seen that images can be modeled using the same architecture. So in this video, we're going to see how a joint model can be built that allows us to relate images and language together. So we've seen that transformers are probably the most powerful models we've got for understanding text and images, and a joint model is useful for tasks like image to text generation. So if we want to condition generative models to create text from image or image to text, or if we want to do image captioning or something like that. So the question is, where can we get training data to train a joint model? Well, one option is to just go and mine images from the internet and whatever surrounding text they have, so captions or some other descriptive text near the image. But there's a problem with this. It's not realistic to expect a model to produce the exact caption that came with the image. So for a given image, there's probably hundreds of plausible captions. And there's nothing to say that a different caption is wrong, it's just different to whatever the original one was. So this paper, CLIP, which stands for Contrastive Language Image Pre-Training, has a really neat way of getting around this problem and learning a really powerful joint model of images and language. So the idea is to simultaneously train a text encoder and an image encoder. In practice, these are transformer models, very similar to what we've seen before. So you feed in either a sequence of text tokens or a sequence of image patches represented like tokens. They pass all the way through the transformer, and then we've seen how we can take one token, so usually this class token, as the sort of global representation of the sentence or the image. Another option as well is to just do something like mean pooling across the output vectors for each of the tokens. Okay, so this text encoder is going to take a sentence and it's going to encode it to some vector. And the image encoder is going to take an image and encode it also to some vector. What we're going to do during the training is force these two vectors to lie in the same space, so to share a common embedding space. So what does that mean? Well, it means that if I embed a caption that describes an image and then I embed an image, if the two things have the same meaning, so this caption is a good description of this image, then they should embed close together. And if they're different, they should embed far apart. So how can we make that happen? Well, what we do is we choose a batch of images along with their corresponding captions. And ideally, this batch will contain images with different content, so that we don't expect the different images to embed close together. And then what our loss function does is it tries to maximize the similarity, where similarity is measured by just the dot product between the two vectors. So maximize the similarity of the correct pairs. So there's going to be n of those for my batch of n images. So those are along the diagonal. So image 1 corresponds to caption 1. I want that dot product to be high. And then I want to try and minimize the similarity of all of the remaining n squared minus n incorrect pairings. So all the off diagonals, in those cases, the caption doesn't correspond to the image and I want them to have dissimilar embeddings. So that's it. That's the idea. We use this loss at very large scale. So we train on perhaps billions of images with a very large text and image encoder. So similar in scale to the sort of GPT models that we've talked about before. Now, once you've trained a model like this, you can use it for something very powerful immediately without any additional training. So effectively, we can use this to do zero-shot image classification by just describing the classes. So if I have a set of classes I would like to be able to recognize in the image, so plane, car, dog, etc., I can turn that into a caption, something like a photo of a photo of a dog, a photo of a car. I encode that sentence, and I encode each sentence for each of the classes I want to be able to recognize. That gives me a set of n embeddings representing these different classes. Now, if I've got an image with some unknown class, like in this case it's a dog, I can encode the image with my vision transformer. That gives me an embedding representing the image, and now I can compute similarities, dot products, against all of the previously computed caption embeddings, the class embeddings. And now I just find the one with the highest similarity. That matched to a photo of a dog, so therefore I would say that this image is of class dog. So you can see this is incredibly powerful. Anything we can describe in text, we can now potentially classify or recognize in images. Even though our model was never specifically trained for that purpose, it's just learned this general information about how the visual world relates to concepts in language. So they did some evaluation of this model, and they tried exactly that sort of zero-shot classification using this clip model against a model that was pre-trained on a large data set and then fine-tuned with a linear layer to map to the classes of a bunch of different data sets. So these are all the data sets here. So the ones in green are where zero-shot clip, so clip with no training, outperformed these ResNet 50s that were then fine-tuned specifically for these classes. So you can see in more than half the cases the zero-shot clip model wins, sometimes by a large margin, nearly 30% improvement in score. But that's actually an unfair comparison, because here clip's being used zero-shot, whereas the other methods have been fine-tuned on some number of images. So if we try to now make the comparison fairer, we can see this comparison in a more useful way. So now we've got over here on the x-axis, we've got the number of label training examples per class that's available for fine-tuning before you do this evaluation. So only clip can do fully zero-shot, so it's got no examples at all, it's just got the text describing the class. That's already giving us about 62% accuracy across these different data sets, so average score. Now we've got a bunch of other methods here which are fine-tuned on an increasing number of labeled examples per class. You can see as you get more labeled examples, this fine-tuning works better. But even when these other methods have been fine-tuned on as many as 16 images per class, they're still only just matching clip's performance zero-shot. And if you also give clip this ability to fine-tune, so you apply basically a linear projection to clip's features before you do this classification, it actually makes it worse when you've got very few images. That's because it's already got a very good model which is being disrupted by this fine-tuning on a small number of examples. But once you get above 8 examples per class, you can push the performance even further, above 70%.